AI today runs on hardware that was never designed for it. Every modern model, from simple image classifiers to giant language systems with billions of parameters, sits on top of infrastructure built around moving electrons through metal wires. Those electrons switch on and off trillions of times per second, but they pay a price for every move they make: heat, resistance, and enormous power consumption. As the models grow, the cost grows even faster. Entire data centers now spend more energy cooling their chips than actually running them. Training one large-scale model can consume as much electricity as several thousand households use in a week. And yet, even with all that power, the process is ultimately limited by physics. Electrons can only move so fast. Wires can only pack so tightly before interference becomes unbearable. And GPUs can only scale until the communication between them becomes slower than the computation itself. A group of researchers has now demonstrated a fundamentally different approach. Instead of pushing electrons through logic gates, they send carefully shaped waves of light through an optical system that performs the equivalent of neural network math in a single physical event. The core idea sounds almost too simple. Encode data into light, let the light propagate, and collect the transformed result. But this simplicity hides something profound. While electronic chips must process matrix multiplication step by step, an optical system can perform equivalent operations because of how light naturally interferes, diffracts, and transforms as it moves. The heavy lifting is done by the physics itself, not by billions of transistor toggles. This breakthrough sits at the center of a field known as optical computing. It takes advantage of the fact that photons do not behave like electrons. They do not experience resistance, they do not suffer energy loss in the same way, and they can carry many channels of information simultaneously by using different wavelengths or phases. When light travels through a lens, a modulator, or a carefully engineered diffractive structure, it performs mathematical transformations at the speed of propagation. In other words, the physics that shapes the light also performs the computation. This allows certain types of neural network operations, especially large matrix multiplications, to be carried out in a single pass instead of millions or billions of digital steps. But before diving deeper into how this works, it is important to understand why our current AI systems are demanding so much from traditional electronics. Neural networks are built almost entirely on massive grids of numbers being multiplied together. These operations dominate both training and inference, and every one of them requires moving data through memory, flipping transistors, and synchronizing results across multiple processors. Even the most advanced GPUs eventually run into the same fundamental bottleneck. Moving data around becomes more expensive than computing on it. And this is precisely where light behaves differently. Photons can carry information without being slowed down by resistance, and they can overlap and interfere in ways that naturally correspond to mathematical operations. Optical computing is not a new dream. Scientists explored it decades ago, but only recently have materials, fabrication methods, and machine learning needs aligned to make it practical. What changed is not the physics, but the engineering. We now have modulators that can encode data into light with fine precision, sensors that can read interference patterns at high resolution, and algorithms that can map neural network operations onto optical elements. All of these pieces were developed independently until researchers realized how well they fit together. The result is a system where a laser pulse, shaped to carry data, passes through a structure designed to represent a neural network layer. As it propagates, the light performs the calculation. By the time it reaches a detector, the result is already there. There is no clock, no cycle-by-cycle execution, no repetitive transfer of data through memory. Everything happens in one continuous physical evolution of a wavefront. And now the central question becomes unavoidable. If the physics of light can compute so efficiently, what does this mean for the future of AI? This is the starting point of our exploration, and in the next sections, we will break down how optical computing actually works, what the recent breakthrough achieved, and how this technology could reshape both the speed and the energy cost of artificial intelligence. To understand why this breakthrough matters, we need a clear picture of what slows AI down today. Modern neural networks rely on an operation called matrix multiplication, repeated countless times during both training and inference. Every layer, every attention head, every convolution boils down to multiplying structured grids of numbers. GPUs handle this by organizing billions of tiny electrical switches that turn on and off in precise patterns. But moving data through these switches and between memory banks takes energy, time, and physical space. When engineers talk about AI scaling challenges, this is what they mean. The math itself is straightforward, but shuffling data to the right place is expensive. The physical limits become even more visible when models stretch into billions or trillions of parameters. Connecting hundreds or thousands of GPUs together introduces another bottleneck: communication. Even if each chip is fast, sending data between them often takes longer than performing the computation itself. It is like having a room full of brilliant mathematicians who work quickly but constantly wait for each other to pass notes. As models grow, the wait time grows faster than the math. This is the point where many research teams have concluded that a new type of hardware is needed. Optical computing steps into this problem with a fundamentally different strategy. Instead of pushing electrons through circuits, it uses photons, the particles of light. Photons do not generate the same kind of heat as electrons because they do not lose energy through resistance. They can also occupy many channels at once, such as different wavelengths or polarizations. This gives optical systems a natural form of parallelism that electronic chips can only imitate with complex architecture. When a beam of light is shaped to carry information and passed through a specially designed optical element, the resulting interference pattern corresponds to mathematical operations that neural networks use constantly. The recent breakthrough demonstrates something even more dramatic. Traditional optical accelerators still followed a stepwise process: send data in, perform one transformation, move data, perform another. But the new single-shot tensor computing method changes the sequence entirely. Instead of a chain of optical operations, the entire transformation is encoded into a single structure. Light carries the data, passes once through the system, and emerges transformed. This is not a metaphor. The computation is the physical interaction between a wavefront and a patterned medium. It does not happen in time slices. It happens as one coherent event. To appreciate this, picture data encoded into light as variations in brightness, phase, or color. A modulator imprints the numerical values of the input tensor into the light field. Each position and property of the beam holds specific information. When this structured light enters the optical device, every point of the wavefront interacts with the engineered pattern simultaneously. Unlike electronics, which must process each multiplication separately, optics performs these interactions passively through diffraction and interference. By the time the light reaches the sensor, it already embodies the result of the mathematical operation. The sensor then converts the final light distribution back into digital form. This is the only electronic step in the process. Everything else happens in the optical domain. Because photons do not slow down and do not collide the way electrons do, the operation occurs at the speed of propagation. The device does not heat up from switching activity. It does not require clock cycles. It simply uses the rules of physics to transform one pattern into another. The researchers validated the outputs by comparing them to results from GPU computations and demonstrated significant speedups along with reduced energy usage. This begins to illuminate why many experts believe optical hardware could become a central component in future AI systems. The approach aligns perfectly with the heaviest workloads of deep learning. Most of the energy consumed during AI computation goes toward matrix multiplications and similar linear algebra operations. These are exactly the tasks that optical methods excel at. Instead of performing billions of electronic operations, an optical system performs the equivalent math in a single wave transformation. But before drawing broad conclusions, we must explore both the strengths and limitations of this architecture. Optical computing is powerful in specific contexts, but not universal. It shines when dealing with large, dense linear operations. It struggles with programmability, precision adjustments, and the nonlinear elements that neural networks require. Modern AI relies heavily on activation functions, routing logic, normalization steps, and weight updates. These do not map directly onto passive optical transformations. Informations. This means that any realistic system will combine optical and electronic components. The intelligent question is not whether optical systems replace GPUs, but how they complement them. The future likely involves hybrid pipelines, where optical devices handle heavy linear algebra while electronic chips handle everything else. This division of labor mirrors earlier transitions in computing. GPUs did not eliminate CPUs, they extended them. TPUs did not eliminate GPUs, they added specialized acceleration. Optical computing may become the next layer, enabling performance that pure electronics cannot achieve alone. As we move forward in this discussion, the next step is to examine what tasks optical systems accelerate most effectively. Understanding this will reveal where the technology fits today, where it might fit in 5 years, and how it could reshape the landscape of AI hardware. To see where optical computing fits, it helps to look at the types of operations that dominate modern AI. The overwhelming majority of time, energy, and hardware cycles in neural networks go into multiplying large matrices. Whether it is an attention layer in a language model or a convolution in an image classifier, the core computation is always the same. Take a structured block of numbers, multiply it by another structured block, sum the results, and repeat this across thousands or millions of positions. This is the groundwork of everything from translating text to detecting objects in video. Because optical systems naturally perform linear transformations, they align perfectly with this workload. When light passes through an engineered pattern, the resulting interference can represent the same mathematical structure as a large matrix. This is not a digital approximation of a matrix. It is the physical behavior of the wavefront itself. And that is why large, dense operations map so well onto optical hardware. Consider attention mechanisms, one of the core components of modern transformer architectures. Attention relies heavily on multiplying query, key, and value matrices in different combinations to determine which parts of the data should influence each other. These operations are enormous in scale and must be repeated for every layer of the model. In a state-of-the-art system, this happens dozens of times per input. Traditional hardware computes these operations step by step, pushing values through floating point units and adding them one by one. Optical computing, in contrast, can embed parts of the attention mechanism directly into the structure of the system, enabling certain transformations to be performed in a single propagation. This is why researchers see optical methods as potential accelerators for transformer-based models and large-scale sequence processing tasks. Another domain where optical systems excel is convolutional operations. Convolutions can be represented as Fourier transforms, and optical lenses naturally perform Fourier transforms as part of their behavior. This means that certain image processing tasks, which digital hardware must simulate with heavy computation, can be handled by optical elements with almost no energy consumption. Historically, this was one of the earliest motivations for optical computing. But today, with deep learning relying heavily on convolution-like operations, the match is more relevant than ever. Of course, optical methods do not eliminate the need for nonlinear operations, which remain crucial in neural networks. Nonlinear functions such as ReLU, GLU, and sigmoid give models their expressive power. Without them, networks would collapse into simple linear transformations, losing the ability to model complex patterns. Because nonlinear operations cannot be performed passively in optical systems, they must be implemented electronically or through hybrid photonic-electronic modules that introduce controlled nonlinearities. This is one of the core challenges in building fully optical neural networks. But it is not a showstopper. Instead, it leads naturally to hybrid designs where optics handles the heavy lifting and electronics handles the logic. Precision is another important consideration. Optical systems deal with analog representations of numbers stored in light intensity, phase, or wavelength. These representations are subject to noise, environmental variations, and hardware imperfections. While modern sensors and modulators have improved dramatically, electronic systems still hold an advantage in terms of precise, repeatable arithmetic. For many AI tasks, perfect precision is not required, especially when models can be trained to tolerate noise. But for tasks requiring strict accuracy, optical noise remains a factor. Researchers address this through calibration techniques, error correction strategies, and designs that reduce sensitivity to environmental fluctuations. The new single-shot tensor computing method is particularly notable because it demonstrates high fidelity despite these challenges, showing that precision issues, though real, are not insurmountable. Once the strengths and limitations are balanced, the question becomes how optical devices could integrate into real-world AI pipelines. The most realistic vision involves optical accelerators sitting alongside GPUs in data centers. During large-scale inference or training, GPUs would handle nonlinearities, control flow, weight updates, and memory-bound operations. The optical system would handle massive matrix multiplications, particularly those repeated many times in each layer. This hybrid division mirrors the evolution of other accelerators. Each new technology takes on the tasks it performs best while relying on established hardware for everything else. The next topic to explore is how the new breakthrough actually functions at a deeper level. Behind single-shot tensor computing will make it clear why this system is generating excitement in the research community. It is not merely an incremental improvement over previous optical designs. It represents a conceptual shift in how optical systems perform computation. It compresses multi-step operations into one physical event. That shift from sequential steps to one continuous transformation is what opens the door to orders of magnitude improvements in speed and energy efficiency. To understand how single-shot tensor computing works, we need to walk through the process step by step, but in a way that stays grounded in intuition rather than equations. The key idea is that light can carry information in many different forms at once. Its brightness, its phase, its wavelength, and even the shape of its wavefront can all encode numbers. Researchers use modulators to transform raw laser light into patterns that correspond to tensors, the structured blocks of numbers that make up neural network inputs. This encoding does not require transistors toggling. It is a physical shaping of the light field itself. Once the data is encoded into the beam, the light enters an optical device engineered to represent a specific mathematical transformation. This device might be a diffractive element, a layered arrangement of optical components, or an integrated photonic circuit. What makes the breakthrough noteworthy is that the entire operation that would normally require many digital steps is embedded into this single structure. Instead of sequential operations stacked one after another, everything is merged into one transformation. As the light propagates through the device, the wavefront interacts with every part of the structure in parallel. Each interaction corresponds to a multiplication or summation that would take thousands or millions of steps in an electronic system. This is the meaning of single-shot computation. The light does not pause at each stage, waiting for a clock cycle to advance the process. The computation is the physical evolution of the wavefront as it moves through the engineered medium. By the time it exits and reaches a detector, the final distribution of intensity or phase contains the result of the operation. The sensor then converts this distribution back into digital data. That conversion is electronic, but everything before it happens purely in the optical domain. A major advantage of this mechanism is that it eliminates the need for memory accesses during the computation. In a GPU, the multiplication of matrices requires moving data repeatedly from memory to compute units and back again. In optical systems, the entire transformation is encoded into the structure itself. The weights of the neural network layer are not stored electronically. They are embodied in the optical pattern. As long as the structure remains stable, the operation can be repeated with almost no energy expenditure besides the initial light source. This is why optical methods can deliver enormous reductions in energy per operation. The device consumes energy only to maintain the laser and perform detection, not to execute the computation itself. Another benefit of single-shot computing is scalability. When electronics handle bigger matrices, they require more transistors, more wiring, and more cooling capacity. But optical systems scale differently. Expanding the size of the matrix operation may only require increasing the dimensions of the optical structure or using additional wavelengths to carry more channels of data. Because photons do not interact with each other in the same way electrons do, multiplexing many channels into the same device is far easier. This yields a path to scaling that avoids some of the most stubborn bottlenecks of digital hardware. But this approach also introduces new engineering challenges. The structure must be fabricated with extreme precision. Any physical imperfection could distort the wavefront and introduce errors. Temperature changes, mechanical vibrations, or material inconsistencies can all introduce noise. Researchers counter these problems with calibration algorithms, stable materials, and designs that are less sensitive to small deviations. The new breakthrough is notable because it demonstrates high accuracy even with these constraints, proving that the approach is not only theoretically sound but experimentally viable. The implications extend beyond theoretical performance improvements. They affect the entire life cycle of AI computation. Training becomes more efficient because some of the most expensive operations are offloaded to a system that performs them at the speed of light. Inference becomes cheaper and faster, especially for large models that must be deployed at scale. Data centers become more energy efficient, reducing cooling needs and operating costs. These practical advantages are the reason why many companies and research labs are exploring photonic accelerators and integrated optical components. They are looking not just for incremental improvements, but for new architectures that fundamentally shift how AI is computed. The next question is how this breakthrough compares to more traditional approaches in the broader context of computing history. Throughout the evolution of processors, new technologies have rarely replaced older ones outright. Instead, each new wave has added specialized capability. CPUs handled general purpose. A tasks. GPUs accelerated parallel math. TPUs optimized tensor processing. Optical systems could become the next layer in this stack, providing speed and energy advantages where physics allows. Understanding how this fits into the larger hardware ecosystem will help us ground expectations and avoid overhyping the technology. Throughout the history of computing, breakthroughs have arrived not by replacing old systems outright, but by filling gaps that older technologies could not address. General-purpose CPUs were never designed for the massive parallel workloads required by modern machine learning, yet they carried the field for decades. When GPUs were introduced, they reshaped AI because their architecture happened to align with the parallel nature of neural networks. But GPUs did not render CPUs obsolete, they partnered with them. Specialized chips like TPUs pushed this evolution further, optimizing the operations that neural networks rely on most. Each new architecture addressed bottlenecks that previous designs struggled with. Optical computing follows this same trajectory. It is not positioned to replace electronic hardware entirely, but to relieve it of the heaviest, most repetitive tasks. When we look at optical systems through this historical lens, their value becomes clearer. They are not meant to handle logic branching, memory management, or control flow. These tasks are still best suited to traditional silicon-based processors. Optical systems thrive when performing large, dense transformations that electronic chips struggle to execute efficiently. Instead of seeing optical computing as a competitor to GPUs, it makes more sense to see it as a complement, a highly specialized accelerator that takes advantage of physical principles electronics cannot replicate. One of the most exciting aspects of the optical breakthrough is how naturally it fits into the architecture of transformer models. Transformers rely on repeated matrix multiplications between queries, keys, and values. These operations dominate the computational footprint of modern models, from language understanding to image generation. Because single-shot optical devices can embed entire transformations into a fixed structure, they can accelerate these operations dramatically. It becomes possible to process large blocks of data in one optical event, reducing latency and energy consumption. For large-scale inference, where repeated responses must be generated in real time, this advantage could transform how models are deployed. Even in training, where weights must be updated iteratively, optical accelerators can provide a major boost. The linear components of the forward pass and backward pass represent a significant portion of the computational load. Offloading these components to optical hardware frees GPUs to focus on nonlinearities, gradient updates, and memory-dependent tasks. This hybrid workflow mirrors how CPUs and GPUs currently share responsibilities. The GPU handles the parallel math, while the CPU orchestrates the process. In a future system, optical accelerators could handle the heaviest linear operations, while GPUs manage the flexible and dynamic components. However, it is important to address the limitations openly. Optical devices cannot easily be reprogrammed to represent entirely different operations. While digital chips can load new weights instantly, optical systems require physical adjustments or reconfigurations. Some designs use programmable modulators to change optical patterns dynamically, but this adds complexity and can reduce the raw performance advantages. The breakthrough demonstrated in research labs shows that stable, high-fidelity optical computation is achievable. But scaling this to fully programmable systems remains an engineering challenge. This is one of the reasons why optical systems are most promising as accelerators rather than replacements for general-purpose AI hardware. Precision also remains a topic of active research. Electronic systems have decades of refinement that allow them to handle numbers with high accuracy and consistent behavior. Optical systems must contend with noise from environmental variations, mechanical vibrations, and imperfections in materials. While models can often tolerate noise, especially when trained with it in mind, some applications require exact precision. For these tasks, optics may not be ideal. That said, researchers have made significant progress in improving the signal stability, calibration algorithms, and sensor accuracy needed for high-fidelity optical computation. The new single-shot method shows that it is possible to achieve impressive precision even at this early stage. Energy efficiency is where optical approaches shine brightest. Because passive optical elements do not consume power during computation, the energy cost of the math itself approaches zero. The primary energy expense comes from generating light and reading the resulting patterns. Even with these costs, the overall consumption is dramatically lower than what GPUs require to perform similar tasks. This efficiency is becoming increasingly important as AI models grow in size and as data centers consume a rising share of the world's electricity. Reducing the energy footprint of AI is not simply an optimization, it is becoming a necessity. Optical computing provides a path toward more sustainable AI development. With these strengths and challenges in mind, the natural question becomes, how soon will we see optical computing in real-world products? Research breakthroughs often create excitement long before practical hardware becomes available. But the ecosystem around optical acceleration is closer to maturity than many people realize. Photonic chips are already used in telecommunications, signal processing, and specialized sensor applications. Companies working on optical AI accelerators have prototypes capable of performing inference tasks at competitive speeds. As electronics reach their physical and economic limits, the incentives to integrate optical components grow stronger. The path from lab demonstration to commercial adoption is becoming clearer. The next segment of this discussion focuses on the timeline of adoption and the steps needed to transition optical systems from research benches to large-scale deployment in AI data centers. Understanding this timeline will help separate hype from realistic expectations and show where the field is heading over the next decade. When considering the timeline for optical computing, the most important point to remember is that breakthroughs in hardware rarely appear suddenly in consumer devices. They follow a gradual path of refinement, integration, and scaling. The recent single-shot tensor computing demonstration is a research milestone, not a commercial product. But milestones like this signal the beginning of a transition, one that unfolds over several phases. The first phase is the proof of concept stage, which we are seeing now. Researchers have shown that it is possible to encode tensor operations into a physical structure and compute them effectively at the speed of light. This phase involves experimental setups, benchtop equipment, and academic publications. These systems are often large, delicate, and calibrated with high precision. Their purpose is not to be practical, but to validate the underlying physics and architecture. This stage is essential because it determines whether a concept is viable at all. Optical computing has passed this phase with compelling evidence. The second phase involves engineering prototypes that bridge the gap between scientific discovery and manufacturable technology. This is where integrated photonic chips begin to take shape. Instead of lenses and free space optics, companies and research groups build on-chip versions of the same principles. These chips use waveguides, modulators, phase shifters, and detectors fabricated using processes similar to those used in semiconductor manufacturing. The goal is to create compact, stable, and scalable devices that could eventually be produced in large quantities. Several companies are already working on photonic accelerators aimed at specific AI workloads, particularly inference tasks that rely on repetitive matrix multiplications. These early prototypes are limited in programmability, but demonstrate clear performance benefits for the operations they are designed to handle. The third phase is integration into existing computing ecosystems. AI hardware cannot function in isolation. It must work with data pipelines, memory systems, training frameworks, and model architectures. This is where optical accelerators begin appearing alongside GPUs in data centers. The hybrid workflow becomes practical. Optical devices handle dense linear algebra, while GPUs handle nonlinear operations and control logic. When properly integrated, this combination can reduce latency, increase throughput, and significantly lower energy consumption. In this phase, the emphasis shifts from showing that the technology works to demonstrating that it improves real-world performance at scale. Companies begin to measure cost savings, compute efficiency, and operational stability. If these benefits are substantial, adoption accelerates. The fourth phase involves scaling the technology to mass deployment. Once photonic chips become stable, cost-effective, and compatible with AI frameworks, data centers adopt them in larger quantities. At this point, economies of scale emerge. Manufacturing costs decrease, packaging improves, and hardware becomes more reliable. The industry develops standards for interfacing optical accelerators with electronic systems. Software frameworks evolve to support hybrid computation seamlessly. This is the phase where users no longer need to think about optical computing explicitly. It becomes one more layer in the hardware stack, silently accelerating tasks behind the scenes. Historically, this phase can take years, but the increasing demand for AI performance and the rising cost of electrical computation may accelerate the process. The final phase is widespread adoption and diversification. Optical computing expands beyond data centers into edge devices, specialized equipment, and new types of applications. Photonic sensors, optical signal processors, and integrated AI accelerators begin appearing in places where traditional GPUs cannot operate efficiently due to power constraints. Telecommunications, medical imaging, robotics, and scientific instrumentation all benefit from fast, low-energy computation. In the long term, optical methods could even influence the design of future AI algorithms, encouraging architectures that align with the strengths of light-based computation. This phase is the point where optical systems stop being a niche accelerator and become a standard component of advanced computing. Based on current progress, the first 3 phases could unfold over the next 5 to 8 years. We are already well into the proof-of-concept stage, and engineering prototypes are emerging steadily. Integration into hybrid systems may arrive sooner than expected due to the pressing need to reduce the energy footprint of AI. Data centers are reaching thermal and electrical limits. Power grids in major tech regions are strained by the exponential growth of computational demand. As the cost of scaling silicon-based hardware continues to rise, the economic advantage of optical systems becomes a decisive factor. Photonic accelerators do not need to outperform GPUs in every task. They simply need to deliver significant savings in the operations that dominate AI workloads. The timeline ultimately depends on a combination of research progress, manufacturing readiness, and market pressure. But the direction of travel is clear. The computing industry is moving toward heterogeneous architectures. Just as CPUs, GPUs, TPUs, FPGAs, and custom accelerators coexist today, optical computing is poised to join that list. Its role will grow as the technology matures, bringing us closer to a future where AI runs not just on silicon, but on the physics of light itself. With the timeline in perspective, we can now step back and examine the broader implications. Optical computing does more than make AI faster. It changes the trajectory of computational energy use, influences how large models can scale, and contributes to the debate on what kinds of intelligence future systems might achieve. These themes shape not only the technical landscape, but the social, environmental, and philosophical dimensions of AI. Understanding them gives us a complete picture of why this breakthrough matters beyond raw performance. The broader implications of optical computing reach far beyond hardware performance. One of the most pressing issues in modern AI is energy consumption. As models grow larger and more widely deployed, the energy required to run them has expanded at a rate that outpaces improvements in chip efficiency. Some estimates suggest that global AI workloads could consume a significant portion of available electrical capacity within the next decade if current trends continue. This is not only expensive, but environmentally unsustainable. Massive data centers require power for both computation and cooling, and the environmental footprint grows with every new generation of models. Optical computing introduces a fundamentally different energy profile. Because passive optical components do not consume energy during the computation itself, the power required is drastically lower. The main cost comes from generating the initial light and reading the output. Even with these factors included, the overall energy footprint is orders of magnitude smaller than equivalent GPU operations. This shift has profound implications for sustainability. Reducing the energy cost of AI could enable continued growth in model capability without overwhelming electrical infrastructure or increasing greenhouse gas emissions. It also makes AI more accessible to organizations that cannot afford large-scale GPU clusters. Another implication relates to model scaling. In recent years, model performance has grown in tandem with size. Larger models with more parameters and more data tend to perform better across a wide range of tasks. But scaling has diminishing returns when hardware cannot keep up. Even if a model is theoretically capable of exceptional performance, training it may be impractical due to the time and energy required. Optical computing changes this equation by enabling faster and cheaper linear algebra operations, which are at the core of both training and inference. If these operations become dramatically more efficient, the ceiling on model size rises. We may see models that were previously unattainable become feasible. This raises exciting possibilities for AI capability, but also introduces questions about how far scaling should go and what safeguards are needed to manage increasingly powerful systems. The discussion of scaling naturally leads to the topic of artificial general intelligence, or AGI. Some researchers argue that computational bottlenecks are among the main obstacles preventing models from reaching levels of reasoning and generalization that resemble human intelligence. If computation becomes dramatically cheaper and faster, these obstacles may weaken. Optical computing alone will not create AGI, but it removes one of the major brakes on scaling. Combined with algorithmic advances, it could accelerate the development of systems with far greater capabilities. However, this possibility must be approached with caution. More powerful AI systems bring not only potential benefits, but also risks related to alignment, safety, and social impact. Faster hardware shortens iteration cycles, enabling rapid development, but also reducing the time available to assess and manage risks. This makes responsible deployment and thoughtful governance more important than ever. Beyond AI-specific themes, optical computing also has implications for other fields. Any domain that relies on large-scale numerical simulations could benefit from faster linear algebra. This includes scientific research, climate modeling, physics simulations, and medical imaging. In these fields, reducing computation time by an order of magnitude could accelerate discoveries, improve prediction accuracy, and lower the cost of experimentation. For example, climate models that currently require massive supercomputers could run more frequently, producing finer-grained forecasts. Medical imaging systems could analyze data in real time without relying on bulky electronic hardware. Optical processors could also play a role in future telecommunication systems, enabling faster signal processing and more efficient use of bandwidth. However, all these potentials come with practical considerations. Optical systems require precise fabrication, stable alignment, and high-quality materials. They must be integrated into existing software frameworks and data center architectures. They must prove reliable, maintainable, and cost-effective at scale. The engineering challenges are significant, but so are the rewards. The trajectory of research suggests that these challenges are being addressed steadily, driven by a combination of academic innovation and industrial demand. As the ecosystem around optical computing grows, tools and standards will emerge to support widespread adoption. At this point, it becomes important to summarize the practical takeaways for viewers, especially those who are following the development of AI or working in technology-related fields.
Optical computing is not a distant science fiction concept. It is an emerging architecture with demonstrated potential to transform how we compute. Its strength lies in accelerating the operations that form the backbone of modern AI. It does not replace electronic chips, but complements them, creating a more efficient and scalable computational stack. Its impact will become increasingly visible in the coming years as prototypes mature and hybrid systems reach production environments. For developers, researchers, and enthusiasts, understanding the principles of optical computing provides a window into the future of hardware. It prepares them for a world where computation happens not only through silicon transistors, but through the physics of light. With the practical takeaways in mind, the next portion of the script will synthesize the main lessons, reinforce the significance of the breakthrough, and provide a thoughtful conclusion. This final section will tie together the themes of performance, energy, scalability, and responsible innovation, offering a clear perspective on how optical computing fits into the evolving narrative of AI.